Hello, my name is Noam Rosenthal. I'm a PhD student at UCLA's Institute of the Environment and Sustainability, and I've been working with the company Cloudistry to provide advanced flood analytics to government stakeholders around the world. Today, I'm going to share work we've done in communicating flood risk in near real time with categorical risk rankings. I'll be sharing a case study of our work in the northern region of Ghana for the country's National Disaster Management Organization following a flood event that occurred in September of 2018. Hello, my name is Noam Rosenthal. I'm a PhD student at UCLA's Institute of the Environment and Sustainability, and I've been working with the company Cloudistry to provide advanced flood analytics to government stakeholders around the world. Today, I'm going to share work we've done in communicating flood risk in near real time with categorical risk rankings. I'll be sharing a case study of our work in the northern region of Ghana for the country's National Disaster Management Organization following a flood event that occurred in September of 2018. When a company like Cloudistry maps a flood event for a client, it's important that the delivered map communicates the severity of a flood in a way that's clear and concise, something that can signal in general terms the urgency of response needed. To illustrate, if someone were to see a map of flooding, as in the image being displayed here, the recipient would have no way of knowing how this compares to previously observed flooding and whether this event can be considered normal or something that requires more serious attention. This high-level, first-glance indicator of risk is what we set out to build for the flood stakeholders we serve. Now, those who work in hydrology and flooding are probably familiar with the concept of return periods, where flood risk and flood severity is measured by the time interval between observed events in a given location. Under this framework, an area that has flooded once in the last 100 years is considered to have a 100-year return period, and it is presumed that any natural event which results in such rarely observed flooding must be more severe. While informative, this framework has long led to confusion and the underestimation of risk. For one, it can give the false sense that 100-year floods can only occur once every century, when in fact, floods are independent events, and a so-called century flood can occur many times over a 100-year period. It can also happen 0 times. Much like flipping a coin, getting tails doesn't mean the next toss will land on heads, and the same goes for floods. Return period frameworks are also challenged by climate change, where a pre-carbon history cannot reasonably predict a post-carbon present or future. Finally, return periods won't say anything about how large of an area was flooded and the adaptive capacity of the areas which were flooded. These are all critical pieces of information for crisis managers on the ground and the social systems that implement relief and recovery. Fortunately, satellite-based flood maps allow for a more granular and responsive measure of flood severity that can address these shortcomings. The approach we take at Cloudistry is to analyze the complete satellite record of flood events for each pixel, as provided by the longest-serving satellite system, Landsat, and we identify the percentage of years in the historical record in which each pixel experienced flooding. This produces our flood frequency map, or what we call recurrence. Once we measure recurrence from Landsat, we can take any new near real-time flood event and overlay that flooded area on our recurrence map to see whether pixels that are flooded in the event of interest are ones that have commonly flooded or have rarely flooded in the last 30 years. When we've linked our observed event to the historical record, like the map of flood severity on the far right here, we can get a sense of the historical frequencies associated with our new event. Getting to this final output, however, is not as easy as it seems at first glance. That is because to produce the most accurate flood maps, we often need to combine data from different satellites. This is for good reason. By combining satellite data, we make sure that we can get imagery as quickly as possible after an event has occurred, and we reduce the likelihoods of clouds obstructing our image. But combining satellite data is not straightforward. Different satellites have different sensor technologies that respond in their own way to conditions on the ground and capture information with varying spatial granularity. That is to say that they see flooding differently. Further, the satellites that inform our historical flood maps from 30 years ago use different technologies than the satellites we use to measure flooding today. And so before we can combine different satellite data into a single flood map and compare that flood event map to the historical record of flood recurrence, we need to account for these differences. Otherwise, we'll be conducting an apples to orange comparison. To illustrate, this frequency distribution shows the number of flooded pixels that were observed by different satellites for the same event. It features Landsat 8 and Sentinel-2, optical satellites that detect natural radiation from the sun, as well as Sentinel-1, which uses its own radar signal to detect water. On the same day and in the same area of interest, we see here that the satellites have noticeably different distributions. Specifically, the radar satellite in yellow observed many more inundated pixels that have flooded more frequently in the historical record. By contrast, Landsat 8 and Sentinel-2, our optical satellites, are more likely to detect water in areas that are less frequently flooded and may present greater risk to communities. It's worth noting that when we roll up these pixel values according to Ghana's administrative boundaries and take the average of the pixel recurrence values inside these boundaries, we see that the discrepancies persist. The y-axis on this scatter plot, which represents the average recurrence detected by Sentinel-2, our optical satellite, and the x-axis, which plots the corresponding value for its radar counterpart, again illustrates how radar satellites overpredict recurrence or underpredict flood severity. In theory, the linear relationship I show here could actually be used to calibrate one satellite's measured flood severity against another's, achieving our aim of harmonizing these disparate sources of data. However, the degree to which satellite measurements differ will also be influenced by variables like topography and vegetation cover, such that no one linear model will always be able to accurately correct for the differences between satellites. And indeed, we found large variability in our early estimates using this approach. Instead, we've discovered that we can achieve the best results using machine learning to harmonize different satellites' flood maps. This method involves showing a computer model, specifically a random forest model, billions of pairs of pixels for any two satellites, and teaching the computer to predict the output of one based on the input of another, all while accounting for secondary attributes like a pixel's vegetation abundance and slope. In our case, we can use the publicly available Sen1 Floods 11 dataset, which contains overlapping radar and optical images from many different flood events around the world to build a rich sample of pixel comparisons. We can run these kinds of machine learning models for many different satellite pairs, and in turn, transform flood maps between satellites so that they can be combined and compared with improved accuracy. This image here shows the result of our random forest model, with the red area representing all the water missed by the radar sensor, but which our algorithm is able to correct for after having been trained on billions of pixel comparisons. The blue and green colors represent areas of water and land that were the same before and after we ran the model to transform or harmonize these datasets. When we compute an F-statistic, which measures the accuracy of our machine learning model, we find a 75% improvement in our ability to classify flood pixels, which not only means that we are accurately harmonizing across sensors, but we're also producing better flood maps. So to go back to our risk ranking approach, now that we've identified a way to harmonize our different satellite sources, we can not only create more timely, cloud-free flood maps that leverage multiple satellites, but we can calibrate these flood maps to match our Landsat historical record, allowing for an apples-to-apples comparison. Once we've intersected our harmonized flood event with the historical record, we can then begin to perform different summary statistics on the intersection to develop a high-level sense of severity that can then inform response. Notably, the choice of statistics should be informed by the beneficiary of the information. Are managers most concerned about the worst observed flooding no matter how much? Or is it more important for them to understand which areas experience this flooding and how large those areas might be? These kinds of questions should ultimately guide the approach taken to summarize an event. For example, by computing the mean recurrence values of a distribution like the one shown here, we would be sensitive to small areas of severe flooding. By contrast, the median or modal recurrence value will grant less weight to the tail-ended recurrence values and will offer an estimate of the most commonly experienced flood intensity. In any case, our team has found that this methodology should be informed by the user of the information, where the user can define preset risk thresholds that are ideally informed by previously observed flood events, such that we can then benchmark against to determine a suitable risk ranking, much like the dashboard shown here. In closing, I hope to have given you a valuable overview of the strong potential for satellites to communicate flood risk to flood stakeholders at a granular scale and in a way that can flexibly accommodate their needs. And that in order to leverage these strengths, remote sensing scientists must find a way to harmonize different sources of data so that they can both create accurate flood maps and compare those flood maps to the historical record. Fortunately, machine learning powered by newly available data sets that document the relationships between sensors provides a methodology of superior accuracy and allows for seamless intercomparison between newly observed events and the historical record of flooding. Finally, once we've harmonized our data, the way in which we summarize the measured severity and the thresholds we benchmark against to categorize risk should be informed by the user. Because it is by centering the user that we are able to ensure that our science can be put to effective use and help improve lives. Thank you.